This talk is already going viral on Wired, if you've seen it. About 30 minutes ago, I think it just got posted. Does anybody know the reference here? Anybody? James Bond, there you go, Las Vegas. Without further ado, diamonds are for hackers. The Prime Minister of Canada. And Miss Victoria.
Thank you. Oh, after you.
How do I move it? Oh. Oh, right, okay. Hello. Welcome. Okay, so I'll start off with giving a bit of a context of why we're here. If anyone wants a little preview, get a bit ahead, here's a QR code for you. We'll share the information later, so don't fret, or just Google Quantum Village, Uncut Gem, something should come up. A little bit of context from where we're coming from. We are both the co-founders and co-organizers of Quantum Village and Quantum Village at DEF CON. So we're a 501c3 as well. We are very fortunate to have lots of people come from all over the planet to join us and look at like the wonderful worlds of quantum technologies alongside cybersecurity and creativity. Oh, yeah. So, a little bit about ourselves. I'll hand it over to Mark.
Okay. So I'm not actually the Prime Minister of Canada. I'm really sorry if you're expecting that. My name is Mark. I've been, when I was 15, I was told that how I use computers is called hacking and I should be really careful. And ever since then, it's been an up and down sort of tryst between being a violinist, which I was for a good few years, and then actually sort of breaking things and doing tech things, and then ultimately also doing a lot of mathematics. I ended up getting a PhD in math, which is really quite fun. I thought it was anyway. And now, like, I'm working with Victoria, and we're working with lots of other cool folks to really sort of bring quantum tech to the fore. So over to you.
Okay, so on the other side, I went to art school. So for anyone out there who doesn't come from like a classical engineering or sciencey background, I hope to be a representation of some hope that you can partake in this field. I've worked in things like finance, everyone's got to pay their dues, and as well as like other companies, and basically worked on commercializing machine learning models for cybersecurity, which kind of got me here. Yeah. A little bit again about Quantum Village, just to give you an idea of like the visual beautifulness of it all, that we're expanding. We do lots of open source projects, and we also have got a zine. So if you're inspired, please submit something, because we want to show how awesome this community is. The real big thing and the mission of Quantum Village is really showing how we can harness that creative misuse for better quantum tech. We really believe that everyone in this room is part of that in terms of the skill sets that obviously get asked after technology is not developed, not before. So why a quantum center? Why Uncut Gem? Well, a lot of it actually stemmed from not being able to get our hands on quantum hardware. So, a bit of constraint usually breeds a lot of good creativity. And if people were coming forward with lots of quantum sensors, we'd probably just be demoing those. A little bit of, background again, why quantum technologies, and it would be remiss not to mention quantum computing, because I think that's always on the tip of everyone's tongue, is why. And literally here's just a bit of a slide that's showing like all the big names and the reasons why that computing in a way on this kind of subatomic level might be the future in terms of understanding nature, using nature to kind of compute nature. So a little bit of overview again on the hardware architecture that's evolving around us. Here we've got a picture of a transistor. All these game-changing kind of epochs that are sort of like coming along. And, we've stuck the chandelier here. Arguably, that's not really the QPU. It's usually tiny. But these are the things that I think, we're on this journey and we really see the hacker community as being part of it. And again, we're moving into this new evolved data center where we're moving away from like a parallel way of computing into this more like probabilistic way. Okay, so in terms of like quantum tech, one thing we always say is we're entering quantum 2.0. We actually had a kind of like quantum 1.0 in the mid-50s, right, in the last century. Probably the best example is looking at the MRI machine. You know, that's a diagnostic tool that a lot of us have probably used, or we've got family members who've used. And actually now with the next advance of quantum 2.0, we're getting devices, these higher precision devices that mean that you don't necessarily need like a shielded room. And that's like the kind of game-changing thing that we're trying to showcase and bring more people into using as well in their everyday work. And again, this is just to show you like the seesaw and the tension between moving science out of the lab into tech, you know, and we really think we're on this journey right now. And this slide is basically explaining that, you know, when you look at a quantum computing stack, for anyone who's curious about it, it's actually deceptively classical. Like from the outside, you might think that perhaps it's, you know, PhD in physics requirements, but, you know, even with a lot of the talks that we've had at Quantum Village and like people we've interacted with who are building these computers, a lot of them are RF engineers, they're software devs, they're not necessarily the sort of archetypes that we might associate when we think of figures in quantum computing. In terms of like where we're at, this is a very crude overview in terms of like looking at that classical open source stack that tends to be dominated by a lot of big tech, but also you've got like RISC-V architecture, like open source architectures. And now we're starting to get kind of like this open source architectures in the quantum tech stack, and we're trying to push that forward even more. Here are two people who've actually presented at Quantum Village, and we're very proud to say that, and that's Max Alto and Jan Alan, and they're two people who are building these sort of open source hardware devices. You know, with Max, it's a magneto-optical trap, a MOT that reduces the cost significantly for labs to be able to perform lots of experiments, and Jan's demonstrating how you can do like an education platform around quantum networking. And these are live projects. I encourage you to get involved if they're piquing your interest. In terms of what else is out there, there's Open Quantum Design, which comes out of Canada. Maybe Mark's got a link, I don't know, Mark Carney. You know, and they're starting to do like an ion trap open stack offering. Encourage you to get involved. So when we've been, you know, again, like the premise of this project was very much like we can't get access to hardware. And like for anyone in this room, like you probably love hardware too. So like we started looking and, you know, you can see there are sort of very like significant established projects coming out of national labs and so on. But when we kind of like dive deeper, they still have this like 10K requirement. And that's quite a lot when you're dabbling around and you might not be government funded or whatever, or I don't know, be an heir to something. And so like even looking at, say, Fermilab, they've got a really nice sort of like open source quantum control system. And you can buy this as well, but again, it's in thousands.
Did you leave the password?
Someone did, but I think we've been on it to remove that. And then, so like, let's move forward now into like the more like quantum sensing. A lot of it is thinking about lasers and cool optics. And actually, when you think about quantum sensing, usually you'll see a kind of like an optics table. And here is a sort of demonstration by Patrick from the University of Nottingham. And I just want to like do a big shout out because there are people in academia that will come to a B-Size London, pitch up for 3 days and show people, and it was one of the most encouraging experiments, and it's really demonstrating that you could do these science experiments with Lego, and I believe a lot of people like Lego, so actually having that shows you how you can open up these techs in a way that you don't necessarily need that fancy optics table. For most people from the physics community, they, you know, working with these like high precision lasers, there is a reason why you have them, but if you're not doing these like high powered lasers, actually for us, it's not necessary. In terms of quantum sensing itself, there are lots of benefits versus classical sensing. And I think that's the one thing to kind of say as well. It's like, it's not just like hype for the sake of hype. There are like advantages in the high precision, and thinking about a lot of them are very, very sensitive. Some other kinds are quite durable as well. And that's the diamond stuff that we're here to talk about. In terms of where we're at, we're looking at these solid state defects. There are other versions that can be used for different kind of modalities and use cases. And here, this kind of chart basically demonstrates that we're going up to that sort of MV Centre Diamond sensor where you can actually detect the heart, right? And then there are other ones where you can do like sort of brain scanning and so on. This is an example of like some very cool companies that are already commercializing, and this is really to show you the potential of the use cases. Like if you're building your own sensor, or you're thinking about like what is the use, like why should I waste my time? And that's really like, you know, robotics, you know, brain-computer interfaces, and medical diagnostics being a big one as well. There are probably some other use cases as well. You can look it up if you're curious, but these are the ones that I think I'm like, wow, these are cool. And then, you know, here's an example of a company called Q-Control that's doing very cool things with an NV Centre Diamond, I think, basically to show like a way of kind of getting around GPS jamming, which is a current issue in the world. So that's something that's really happening. And, you know, it's really about saying there are quantum technologies that are out of the lab now and are scaling and are viable and probably worth checking out. I didn't get the time to put a cute photo of someone wearing this like 3D printed helmet, but basically this MEG sensor, it's not using diamond, it's a different kind, but they're 3D printing it. And it's also from the University of Nottingham, where the MRI machine technology was actually born. So it's showing you that even, you know, the genesis of these devices and how people in industry are evolving. So who else is into diamonds? Because it's not just all sensing. And I think this is the fun bit when you're thinking about this quantum-enabled like tech future. And that's to say that there are people actually using diamonds to compute. So if you get your hands on some, like maybe you can actually like go create your own computer. Maybe not a very good one, but you can get started. And actually, you know, thinking about devices on the edge, actually the interconnects and the networking. And because we can do diamond technology, like NV Centre Diamond technology without cooling, that's the really big thing. You know, you don't need these like chandeliers that you sort of associate with a lot of quantum computing and quantum technologies. That's the real, you know, gift that NV Centre Diamonds do. In terms of open source and like why we felt this project was important and why to open source, I think the really key thing to say is that idea of collaboration. It's incredibly important. It's incredibly important with different skill sets as well. And, you know, I think one thing when I was just researching around Windsurf, he probably doesn't need much introduction to people here, is actually that, you know, I think once upon a time, and maybe Wikipedia is wrong, but he was trying to actually lobby to privatize the internet. So it shows you how people are also thinking differently or changing their perspectives on what should be closed, what should be open. Right. So we're here to present Uncut Gem. You know, just now we've done with a little bit of the context. And the real key things here for us with the design philosophy, as I said before, like kind of this design engineering perspective is really where we're like harnessing and where I think the hacker community has a lot to contribute. The aim for this device is really like for education, for exploration. There's a lot of demand, I think, for that. You know, the idea of also using off-the-shelf components was very important. As anyone knows who's trying to like reproduce things, like it can be like really cumbersome. Like when you're trying to reproduce something, you're like, this is not working. But, you know, especially that for us, and then creating a hardware stack, obviously that allows you to, I guess, you know, with a lot of hardware, you can actually make it a software problem. And actually that's where skill sets, if you're like a machine learning person, an AI person, you can do that post-processing. So it's really to show that like if you're in a different field, like an adjacent field, there's actually something for you. And then we've really simplified it. Like this is not supposed to be the best sensor. It's supposed to be like as cheap as possible and kind of making it as simple and easy for people to get started. All right, I'm going to hand it over to Mark.
Thank you. Okay, so let me give you an overview of kind of how we constructed this device and also what's going on. What is NVC, so Nitrogen-Vacancy Centre Diamond magnetometry? So who here has like seen a Hall effect sensor? They're like 50 cents, about this big. Yeah, loads of people. We use them all the time, right? And this is how they work. So we put a charge across a doped bit of silicon, just as we do with pretty much every other semiconductor. And then if a magnetic field crosses it, the Hall effect means that if we take an orthogonal measurement, we can get an estimation of how strong the magnetic flux, or the Teslas, of that particular magnetic field is, okay? Now, this is basically how we do magnetometry in the quantum sense, but we do it in a very, very different way and with much, much higher sensitivity. So this is an artist's interpretation of what's going on, all right? So we take a diamond lattice, okay, a big carbon lattice, and something happens to energize it. You can irradiate it, you can put it in a cathode ray tube and hit it with electrons. They form naturally, only very small amounts. They form under the elastic deformation of diamond, which gives you an idea about how much energy is required, okay? So what happens is that a carbon gets knocked out. Now a carbon, if you remember from chemistry class, has 4 legs. If a nitrogen, says nitrogens diffuse into the lattice, and so when if the nitrogen takes the place, then the nitrogen having only 3 legs leaves a gap. Now nature abhors a vacuum, is a phrase you'll hear a lot, and so actually that gap is a quantum mechanical thing, okay? And so it has an energy. Okay, it has what's called a Hamiltonian. In fact, one way of looking at it is what's called an isoprobabilistic spin density, aka the pretty picture of the probabilities of measurements in the structure. And the fact that this is actually really quite tight and quite sort of well formed is why you don't need to cool it. Because a lot of quantum systems you need to supercool. Right? With these, you don't. And the reason is that, I mean, they have a very low efficiency. It's about 3%. Other defects have like 60%, but they do require cooling, like tin vacancies. But nitrogen vacancies have a low efficiency, but also they form what's called a virtual atom. And it's a virtual atom, for the technical folk, without a Doppler shift relative to a photon, which basically means they're not vibrating because it's a gap, so it can't vibrate. Right? So the idea there is that actually, you know, we can actually have a very stable platform for doing something quantum embedded inside a very, very robust lattice. Like diamonds are really hard, like they are the hardest thing we have. So actually, it's a very robust material with interesting quantum properties. Now, I mentioned it has an energy, and we may as well just rip the Band-Aid off and show you what that looks like, okay? When someone says, here's the Hamiltonian, this is what they mean, all right? And so let me just break this down. I'm a mathematician, I'm qualified. So we have the energy of the system, all right? And we describe this in a few terms. So these 2 terms describe the energy from light and microwaves. And then we've got this term at the end, and there's 2 capital letters, B and S. This term is a magnetic field tensor, which means that it responds, the energy in the system reacts to magnetism, and then the other side is a stress tensor. So technically, and we haven't done this, but technically you can measure the stress in the lattice using light, okay? So this is basically a crash 10-second course in NV centers. There are YouTube lectures you can go and find, MOOCs about this kind of thing. But for what we need to understand for this build, that's all we need. So we can represent this in much prettier pictures, and so I'm going to give you a walking tour of basically how these centers are interacted with. Okay, so this is the stage. Okay, we start with the lower energy levels, so lowercase ABC, and then we have the upper energy levels, capitals ABC, and we can go up. And when we have a little shelf level, and all of these will come to play in the story. So what we do first is we put green laser light in, about 520, 525 nanometers, okay? That puts it into a very high energy state, and it will relax down to the least greatest energy state here, which is the capitals ABC, okay? So when it relaxes there, it can then wait a while, and then it will want to go into its lowest energy state. So it wants to go back from high to low. Now, if it goes straight down, it will release red light. If it goes down via a shelf level, it will release infrared light, a longer wavelength, because it's kind of expended some of the energy on the way down. It took a little rest, had a little hiatus, little siesta. All right. So actually ABC, those are 3 letters, right? Like what are they doing there? Well, there's a thing called a hyperfine structure. So if we apply microwaves, then we can go from A to guarantee being in B or C. And if we apply microwaves and a magnetic field, we can get all the way up to C. Right? And what that means is we're more likely to have things collapse straight the way down and increase the output of red light. Okay? So that's the kind of system we're dealing with. If you want to read more, there's a paper here. You can also look at things like Zeeman splitting to sort of refine your understanding. I won't go into that now, but basically the physics is really quite straightforward. And I say that as a mathematician. I had more interesting times than the electronics, which we'll cover in a moment. But this is the structure of the output. So you see the sweep in microwave energy. What does that mean? Well, we just, increasing microwave energy is increasing frequency. So we sweep a load of frequencies of microwave energy, and if we choose the right center, we'll see a little dip. That dip is, for reference, 2.87 gigahertz, okay? When we have microwaves with a magnetic field, we will see splitting. And so that one dip will become two dips and then become more dips, and they'll get further apart as the magnetic field increases. So if we can find a way of measuring this, then we can find a diamond that has these properties, then we should be able to do some sensing. At least that's what we thought. Turns out, I think we might have been right. But there's four things we need. Okay, so we need light, we need microwaves, we need to detect red light, and we need a magnetic field. Now, the magnetic field we get for free from the use case, right? We're not going to provide it. We don't want to provide it. We want the other thing to provide it so that we can then set up the system and then measure it, all right? So we're not going to generate a magnetic field. Great. Then the other thing we need is a light source. Now, physicists love their lasers, okay? They love a laser. Physicists will go ape for a laser. They really will. However, lasers have somewhat of a health and safety OSHA nightmare attached to them, which is that you can look at them and then you're blind. Okay? So we don't want to blind people. We want people to, be without being blinded. So we actually sort of looked around, and Victoria was like, can we just use like an LED? Turns out you can. Because actually, if you remember that Hamiltonian, there's no phase term. So actually, because there's no phase term, you can just use the energy from the correct frequency, okay? Now, so we just use some super bright LEDs, and that's the light part sorted. So we need to provide power, a little resistor so they don't blow up, and that's the LED done. All right, great. So far, it's a really simple build. Anyone can do that. They've probably already done it. We mentioned microwaves. Now, microwaves we have a lot of experience with. Most of telecoms is built out of microwaves. Wi-Fi and all these other communication infrastructures, they're all microwaves. So we're really, really good at handling microwaves. Quadrature, phase shift coding, they are really complicated ways of messing around with microwaves. So we have chips like the ADF4351, which is just a microwave generator. You send it 6 packets of data over SPI, and you get the ability to generate a specific microwave frequency. And the range of these things is impressive. It goes from 35 megahertz all the way up to over 4 gigahertz, right? Really huge range. Because they're designed to just be used in general telecoms use cases. And also the amplifiers. So the amplifiers here are kind of like Galley 84, to those who know what that is. They're just monolithic microwave amplifiers. There's a band of frequencies that they work in, usually in a similar range to the chip that's generating them, and they will just amplify. And so we put 2 in a row, and we get, I think it's sort of minus 16 dB or something, which is quite a good amount of amplification. So, okay, this is what we're going to use for this side. Then we need to detect the light. And so you'll hear a lot about photodetectors and photon detectors. And they have an interesting way to be built, okay? You have to make lots of very smart choices. So the first choice we made was the BPW34 photodiode. This is the response curve. Now, remember, the light going in is 525 nanometers. If you draw your finger on the graph, then you'll see that's about 0.2 on the sensitivity scale here, whereas the red light, which is, by the way, 620 nanometers, is about 0.5 on the sensitivity, so it's much more sensitive. So if we take that higher sensitivity and add some filtering, we should have a really good result. But how do you filter things? Now, a physicist will tell you, you have to use a thing called a dichroic mirror. They're amazing, okay? They are basically optically highly polished surfaces, sputtered to a very, very particular level, and what that allows you to do is have a very narrow gate on what frequencies of light you let through. They also cost about 50 quid each, okay, at least. They are not particularly cheap. So, okay, what's an alternative? Last year, I found a paper from, I think, the previous year that showed you can just use red filter gel from Amazon that's used in lighting, and it works 80% as well as dichroic mirror. And we tested that, and it's true, okay? So we have made a great saving right there, okay, all right. So that's, and we have at least one roll left of this at the village. But that's not enough, okay? You need to be able to take the signal from a photodiode, which is really weak, and then amplify it. Now, for that, you use a transimpedance amplifier, and there are quite a few papers in the literature that have transimpedance amplifier designs. Some of them are dreams from I don't know whom. There's no way they would work. I don't quite know how no one spotted it, but hey, whatever. And others were actually really useful and informative. And we were able to set up this little amplification network with a dual op-amp. And we chose the values. You can change them and tweak them, but ultimately, this kind of works, mostly works. We also, instead of using a -5 volt generator, we also use a voltage divider to create a fake ground. So it's a total hack, it's a total cheat, but it saves $10 on the BOM, okay? Because you're just using 2 resistors as opposed to a very expensive component. But if you want to use the proper components and use an INA 217 or some sort of nicer instrumentation amplifier, you can do that too, and you will get better results. We just wanted a baseline, this works. So, how do we do the input-output? We chose the ESP32 because they're basically everywhere. So even if you can't buy one, you can just find a device and desolder it and just take it out, okay? They cost about $4 new. I don't think there's a used market for them because why would you, right? So we use this to control it, and this is really nice. It has a really nice 3-volt ADC, which is actually quite high for a microcontroller maximum threshold for ADC conversion. We also have it also has onboard Wi-Fi and Bluetooth, okay? So it is a connected sensor in all but software, all right? That is actually quite nice, okay? But when I say software, I mean firmware here, and when I say firmware, we wrote it in Arduino. And the reason for that is not because I'm a huge fan of Arduino. I mean, I am, right? Personally, I would write things in different ways because I'm that way wired, but unfortunately, the way I do things is not necessarily portable. So what we did is we chose Arduino. Arduino allows us to have a really wide range of alternatives. If someone says, I don't want to use ESP32, I want to use, or I can only get a hold of this chip, or it's 5 to 10 years down the line, someone wants to just try the code out. Well, what we did is we've exposed all the SPI pins and all the control pins, and we're releasing all the firmware in Arduino. So that way, actually, more people should be able to A, understand the code, and B, be able to actually sort of utilize the code. And we also made lots of decisions along the way. So the default library for the microwave generator chip, basically, you tell it what frequency you want, and it generates all of the arrays. That is really noisy when you've got an op-amp right next to it. So you end up not detecting the diamond, you're just doing a side channel attack on your own microcontroller. That's not ideal. So instead what we did is we pre-computed lots of arrays, and we've got a script we released which actually shows how to generate these arrays of values. And that script then allows us to then just pre-compute the sweeps of microwaves, and then we're just fetching from memory and then just throwing it at the microwave generator. So we're not actually sort of computing it every time, right? That's one kind of design decision that was really important. And so we made a PCB. This is the very first design. And it was great. It looked wonderful. It was just missing one part, the diamond. So as you do, we managed to get in touch with De Beers, because that's a sentence I have in my life now. Actually, it's Element 6, so they're a company who actually do sort of manufactured and composite diamond material. And we also spoke to Adamas Nano as well, and we sort of worked with various companies to try and get some samples of diamonds so that we could actually access and test our design of this thing. So this is where, I'm just going to change to Finder. So here we have, whoops, wrong demo. This one. So this is a chunk of diamond dust. I bought 4 or 5 carats worth of diamond dust, which is intended for industrial applications. You can do this on eBay. I don't know if it puts you on any lists, but hey. So I bought a lot of diamond dust, and I was told, remember the elastic deformation underground? I was like, hey, diamond dust, some of them might have had enough energy to get some MV centers. And this is what happens. This is a red filter with a speck of diamond dust, and it's lighting up. Not all of them do this, by the way. If you try it, not all of them will do this. But as the green laser, so the yellow dot is actually green, and then it hits the diamond and it converts it, and it looks kind of underwhelming, if I'm honest with you. That when you look at it, when you compare it to a proper actual manufactured diamond, this is what it looks like. So here you see the laser come in, and then there's the conversion. There you are. That's lots of red light being converted. This is about 1 part per million. So for every million atoms in the lattice, you've got one center, which means that it's doing all this conversion. Lots and lots of light is being converted from green into red using the nitrogen vacancy centers themselves. So that was actually very cool. So we have a diamond, it's high quality. How do we get rid of the optics table, right? And the idea we came up with was a prism. Right? Epoxy is a really easy material to work with, all right? So everything can be encased in epoxy. Whether it should is entirely up to your own moral fiber. But, you know, you can just get epoxy that'll cure in 45 seconds under UV light and has great optical properties, right? You can literally, people do make lenses, not very good ones, but they make like sort of, you know, quick and dirty, like sort of lenses for certain use cases. And so we went, okay, let's try this. But things to consider, diamond is a stone. It sinks. So you can't just put it in epoxy, it'll just sink all the way to the bottom. So you've got to take that into consideration. Also, you've got to have proper prep and make sure everything's very clean and make sure you've got rid of all the dust ahead of time. But basically, here's the rough plan. So this was version 1, and it was terrible. It didn't work. So this is not close enough for the microwave antenna. The diamond little speck here was not aligned properly. This didn't work. So we went through another design iteration. Okay, put the laser on top, put more red filtering, and then put an amplifier at the bottom. Okay, the amplifier values here, for those of you who want to squint and decode them, no, they don't work. And likewise, the diamond itself, with that pointing directly at the PD, even with all the red filtering, it doesn't really come together. This doesn't work. All right, fine. This did. This was the start of it starting to look like we're getting a signal. And so these are like sort of the right kind of values on the op amp, load of filtering on the power. The laser is kind of just held up by copper wire because actually it's quite malleable, so it's quite easy to work with. And we're just shooting it orthogonally, so the laser beam is missing the photodiode, but it's getting the diamond. And you'll see that it's bright yellow. That's because the camera sensor looks at the red and the green light and goes, that's yellow. It's not. If you look at it up close, it actually looks like it's red and green. But this particular sensor picked it up like this. Okay, this is great. So then we got the PCBs ordered, and we're like, let's try and build one of these. Actually, maybe we should just try this out. And so we did, and it worked. If you look there, you're seeing little dips as we scan. So we scan the frequencies, through the frequencies, and then we take a load of measurements. And as we get up, you see a dip, and it comes back up, and it works. All right? Or at least it seems to work. All right, so this is what it looks like up close, just to give you a closer idea for the build. There's a microwave loop. This is just 24 swig copper wire. Most swigs between 20 and 28 will probably be fine. We're looking at doing an open source, like sort of actual antenna. That would be a really cool thing if you've got the software to do it, but currently we don't. But these are the parts. So the diamond's in the middle, a little loop for the antenna, and then a photodiode is underneath. All right, so this is the kind of overall, the overview of the actual layering, just for those who want to sort of try it at home. We won't spend too long, don't worry. But we put a layer down first, and then we position the diamond on the loop. Then what we do is we secure that, just a thin layer of epoxy. And I'm using UV curing epoxy here because it's actually really easy to work with. By the way, if you mess it up, it's fine. Just get a hot air gun to 200 degrees, then epoxy will denature, the layers will come apart, and the diamond won't care. Okay? The diamond has seen far, far hotter temperatures. It'll just go, fine. So you can just get your diamond out and try again. All right? It's really easy to iterate with this stuff. And then what we do is we secure everything in epoxy on top. It's all orthogonal. Put a little layer where we can secure the red filter. And then what we get out the other end is a working setup. So conceptually, the chip is telling each frequency to the microwave controller. That then generates, as a source, generates it amplified into the aerial. That excites the diamond. We hit it with green light. We actually put the LEDs inside the epoxy prism. And then what we can do is you can just see we filter out the green and then the photodiodes on top, and then we take measurements. So set a frequency, take some measurements, set a frequency, take some measurements, rinse, repeat for the whole array, and then hopefully you see the right shape of the output. If you don't, you need to do more filtering or you need to do more software. So for style points, the first one that you saw a few slides back was actually built out of parts almost entirely sourced on Amazon. for various reasons. And in total, it came in at about $160, right? Like the only thing you couldn't get was the diamond and the PCB. Everything else is on Amazon. It's not just off the shelf. It's so off the shelf, it has a prime option. Okay, so but obviously it's more expensive. If you want to wait a little longer and save a bit of money, that's also an option. AliExpress might be your friend. All right, next big question.
Okay. Does it actually work? I mean, to be honest, when you were describing it just now, I was thinking, okay, if it doesn't work, we can put this on Etsy with all the, little jewelry-esque molds we've been using. So we enlisted a friend, Professor Ben Varco from University of Leeds, to make sure we're not sort of like promoting some sort of snake oil, because there's already enough of that in the world. And we drove up to Leeds. It's not like the most accessible place in the UK, I must admit, as a person from London. But we went there nonetheless, and here it is. We're testing it out because that's where you have all the kit to do it. And here I am literally putting my heart and soul into it, because I was like, okay, like let's find a really useful use case, like my heart. Like you keep saying we can do magnetometry, can we really?
Okay, so to explain a bit of the science here, the blue line, if you notice Victoria's holding two electrodes, the blue line is a standard electrical measurement of the heartbeat, so you see the up and you see the down, right? The yellow line is a heavily filtered, so we took the signal out of the amplifier, put it through about $30,000 worth of filtering equipment, and then we were able to zone in on a particular frequency set, and what that meant was we got the yellow line, which exactly aligned. We were doing magnetocardiography with the design. That's cool. Thank you. Okay. So here's a short demo, just like so, showing you like another way of perceiving it. So here is the gray thing at the bottom is a reference magnetometer. You can see it here. And then there's an oscilloscope, and our device is just next to it. And I take a diamond on a post-it note, because that's how I roll, and I shake it, and the red line is the $5,000 magnetometer, and the yellow line is the not $5,000 NVC diamond magnetometer, okay? So this is actually showing that it can kind of keep up with a reference device. I mean, all in, actually, with the filtering, it probably costs more than $5,000, if we're honest. But this is the goal. We want to get it that we can have a package that allows us to actually come to having this magnetometry available. But ultimately, yes, it works.
All right, so here we are. We're here with the uncut gem, released as a DEFCON badge, because I think always we need to make something with utility. For us, it was to make a badge. That was our description, our brief. And I think for a lot of people outside of that, they were like, why are you doing this? Kind of thing. And actually, the moment we started evolving the design, adding a prototyping piece at the top and so on, whenever I'm interacting with people from our community, they're like, I get this. I understand this. This looks familiar, as opposed to, the really fancy kits you can get in kind of physics labs that you probably aren't getting. And the evolution of this design is really to make it more hackable, accessible for people to be able to use it, and then also make it easier to manufacture. So we're also simplifying the design as well. And this is available. And I guess this is it here. Although obviously it should be wearable, so we will be fixing this soon, right now. Anyway.
All right, so this is kind of a bigger version of what you're seeing here. Also, this doesn't have the cute purple. So I'll just give you a quick walking tour of what we put on this board. So on the right, we have the integrated signal generation and amplifier setup. On the left, we have a reasonably well isolated op-amp. It could do with improvement. It needs a lot of work, but hey, it does work. We also have USB-C because it's 2025, and I think micro USB should die. Sorry, personal opinion. But we also, over that, we also do sort of UART processing. So the readout is going straight out over USB via UART. That is from the mount of the ESP32 and also breakouts. So all the pins, I2C and SPI that you use in this build are all broken out. So if you want to just build one of these but not use the ESP32 and use something else, it's just there. And at the top, you can see 2.54 millimeter pitch pins. If you want to just put something else on here, an accelerometer, some kind of, you know, I don't know, barometer, temperature sensor, whatever you think is going to be useful, you can kind of build that in with a prototyping area. So this is the idea. This is basically the uncut gem V2. Here it is. It's here. So, thank you. So does this work? Okay. Just a quick overview of some of the results we managed to get. So this was the first kind of measurements I was taking. They are bad. In case you're wondering, yeah, we're missing a signal here. That's fine. So we took the data. We did some ambient measurement adjustment. We wrote some Python code. This is all up on the repo, or at least it will be if my laptop sort of sorts itself out later. So we did some ambient adjustment, and then I hit it with a large magnet, okay? Large magnet, like heavy neodymium, probably like sort of a couple of thousand Gauss, like some reasonably strong magnet, all right? And then I put it in this very high-tech isolated chamber. Okay, this was formed from a paper roll and a coaster on a wooden table, all right? So very high tech. And then we did some measurements. This is what we got when we did the ambient adjustment. That's correct, okay? That's good. All right, but does it detect magnets? Okay, large magnet, here we go, yes. So not only did it find a shift, it also lowered the full levels completely, which means that the illumination went right the way up, okay? So actually, this is a really good sign. I thought it was really bad until a professor of physics told me otherwise, Professor Ben. So this was actually really cool. I was like, well, can we hack with it? Because I want to hack things with it. And at the moment, that's quite nascent because there's so much involved in terms of delicately balancing things. But I did get a little LED with a little, and cheated slightly with a coil, and I was able to see this, okay? So the blue line is just reference, and it's a noisy environment, bear in mind, electromagnetically noisy. But when I turn the LED on, you do see the shift of the splitting, okay? So there is promise here for doing some really cool stuff, we hope. And we're releasing all the designs, everything, fully open source. So the PCB, the schematics, if you want to go make your own. In fact, actually, someone in Italy, Davide Gesser, has actually made his own uncut gem. It's so cool, okay? And I think we sent him a diamond to sort of get him going, right? Like, he's such a nice guy. But we are like, you know, really, really excited to sort of have this actually working. This demonstrates that, yes, we can get the splitting, we can start doing better measurements, we can start improving it, and we really sort of want the help.
Yeah, so that's where you guys all come in. We're hoping. I will add one thing that Professor Ben actually did add afterwards, is that he was kind of like, holy CRAP. Actually, I might have been humoring you both a little bit when you were coming all this way. And, you know, I think that's a true testament of what, you know, this community can do. And as you can see here on the slide, we've got an example of the sort of skills that we need to improve, and we're working on. I think you mentioned that it is a connected, we can do like, we can make it into a connected sensor. So that's another thing that actually might be an interesting thing for people to explore as well. And we welcome any contributions and updates, really. So thank you. Access all atoms.
So it takes a village. All right, you know, we've been really guiding this for the last year mostly. We've been looking at doing a badge for 3 years. We really honed in. Yeah, it took a while. Sorry about that. But like, we really zoned in over the last year and really tried to get this working. And we've had some help from some amazing people. So not just myself and Victoria, but also Dr. Matthew Markham, who's been doing this stuff for like 18 years, long before it was cool. Max Shivakar Alto, who's done some amazing fabrication work. There are some 3D printable mounts for which he sent me the STL file, and it'll fit onto the 3 little holes in the middle. We couldn't quite get them 3D printed for today, but that's a supply chain problem. Dr. David Benoit, who is an astrophysicist at University of Hull, he's amazing. He hunts aliens with quantum computers. If you want to go and read about some really cool work, go and find David. He's such a cool guy, and he's been really helping because, you know, astrophysicists are used to dealing with noise, so he's been really helpful there. Rick Alther and David Bengtson have been really helpful in terms of, you know, the electronic works of the RF stuff, giving us some pointers about about sourcing and component selection. So thank you to them. Professor Ben, of course, because he's really cool and let us have a lab for half a day. And also Brian McDermott, who's been a sort of advisor and sort of helper since the beginning of the project. So thank you all to them. And all I can say is here's the end of the presentation and access.
And thank you to everyone here, because this is the space that, like, this is the community that's given us the space to do this.
Yes, thank you all. Access all atoms.